Moving on to conjugate addition reactions. So we're going to remember our aldol condensation reactions can form alpha beta unsaturated carbonyls. Now we want to react these alpha beta unsaturated carbonyls. We want to do conjugate addition reactions, adding to the conjugated pi bond. So thinking about resonance here, there are three resonance contributors. One is where the polar carbon-oxygen double bond will drop a lone pair on the oxygen and a carbocation on that carbon of the carbonyl. We've seen this one a lot. But then with a conjugated alpha beta unsaturated pi bond, we can see further resonance where we put a carbocation on beta. Okay, so resonance hybrid. Let's just talk about that real fast. Delta minus on the oxygen, double bond character all throughout, and then delta plus on the carbon of the carbonyl and on beta. So where we saw an electrophilic position before was the carbon of the carbonyl with a alpha beta unsaturated carbonyl. We also see another electrophile at beta. There it is, two electrophilic positions. Either one can be attacked depending on what nucleophile we use. Grignards are back. Grignard reactions are going to be attacking the carbon of the carbonyl position. This is called 1,2 addition. If we were to count 1, 2, 3, 4 across our alpha beta unsaturated aldehyde here, Grignards will always attack at the carbon of the carbonyl to make alcohols. Gilman reagents, also called cuprates, are more mild nucleophiles. They do not attack the carbon of a carbonyl for an aldehyde or ketone. They will be undergoing what we call 1,4 addition or conjugate addition. 1, 2, 3, 4. They are actually going to be attacking the number 4 position. That will cause a lone pair to kick up on carbon number 3, and that's why we have the acid workup to protonate the resulting enolate. We're going to go through that mechanism real quick. Okay, so general mechanism is going to be looking at undergoing a protonation of an enol. This is what we typically see just because of the ability of oxygen to hold the negative charge better than a carbon group. So when we have a Gilman reagent or a cuprate, that nucleophile that attacks the beta position, what we hypothesize is that enolate that forms will be the more stable resonance form where the oxygen has a negative charge. The acid workup then will protonate that oxygen to an enol. But then we also do know that enols tautomerize, and that will just result with our aldehyde reforming and the proton forming back onto the alpha position. Stronger nucleophiles tend toward 1,2 addition. Less reactive nucleophiles tend to do conjugate or 1,4 addition. Typical enolates often give mixtures of 1,2 and 1,4 additions. So stabilized enolates are what usually give 1,4 addition exclusively. Stabilized enolates come from our dicarbonyl enolates. Those enolates that have 2 carbonyls at the alpha or at the beta position, right? If this is our home plate for our first carbonyl that we're talking about, here's alpha, it has some hydrogens, beta is another carbonyl. Those are the stabilized enolates that actually will help us exclusively do 1,4 addition to another alpha beta unsaturated carbonyl. This is called the Michael addition. A Michael donor is the nucleophile that does conjugate addition, so it will be the stabilized enolate. The Michael acceptor is the alpha-beta unsaturated position, specifically the beta carbon of the electrophile in step number 2. Following Michael donors give exclusively 1,4 addition, so it doesn't just have to be a beta ketoester or a diester. It can be any other resonance stabilized list here in the Michael donors, right? So typical ones are the dicarbonyls, right? But what's interesting is that even having another pi bond adjacent on that beta position is important. So those nitro groups are really, really good because they are so electron withdrawing. They stabilize that enolate very well. Cuprates or cyano groups, the nitrile group as well. Michael acceptors have to have that beta position. All right, so all of these are acceptable, but again, beta position of some electron withdrawing group. The Stork enamine synthesis is sometimes utilized as well, and that is because singly stabilized enolates do not usually give high yield Michael addition. So if you wanted to use this type of a ketone, you really couldn't form an enolate from it and then do conjugate addition. This ketone cannot be the Michael donor. But if you convert it into an enamine, right, this enamine here, you actually can create the conjugate addition much better. So remember, enamines behave like enolates. They are nucleophiles, but an enamine is less nucleophilic, and therefore it's a Michael donor. Super fun. Merging chapter 20 at every waking hour in this chapter. So after conjugate addition, aqueous acid can convert you back to your ketone. All right, so it's not the end of the day to use this Stork synthesis to convert your ketone to an enamine and then do the reaction. Boop, 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 boop. Right? Not only will the aqueous acid convert your enolate to an enol and then tautomerize it back to a ketone, you will also convert your iminium ion, your nitrogen compound, back to the ketone as well. So overall, we see form the enamine and then do conjugate addition at the beta position and then hydrolysis for that enamine back to the ketone plus tautomerization for the carbonyl. Excellent. Robinson annulation. This is a 2-step process that is really there to form a ring via an intramolecular aldol reaction. So first thing that we do, Robinson annulation, is combining 2 reactions that we have seen so far. We are combining the Michael addition reaction and then doing an intramolecular aldol condensation reaction. So we are going to walk through this one right now to make sure that we see both steps playing out. Okay. NaOH is going to be able to take the alpha of the stabilized enolate for the stabilized enolate position, right, to create that Michael donor. Then that Michael donor is going to attack the Michael acceptor. I'm going to call that beta already. Alpha and beta joining forces. Alpha of one, beta of the other. Be very, very careful when you're adding these things up that we are looking at not dropping carbons. Right? Beautiful. And then H2O. Can go and form the enol nice. That enol can then tautomerize to the ketone. Again, I'll just show tautomerization occurring. It is base catalyzed here, which is A-OK. Spread that out a little bit. All right, so there is our Michael addition product. Then what we want to think about with the intramolecular aldol is, can we find the beautiful 6-membered ring intramolecular setup? Typically, it's from the opposite side of the Michael acceptor and then to one of the carbonyls from the Michael donor. 1, 2, 3, 4, 5, 6. There we go. So hydroxide again is going to be used to form our enolate. And then our enolate will attack our carbon of the carbonyl in an aldol addition. Be careful with your structure here. Make sure we're counting up our carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbon number 6. Just going to clean that up. Is what was attacked by the enolate, carbon number 1. Finish up the aldol addition with protonating that alcohol. Don't drop anything. Be very aware of extra carbons. And then we can imagine, here was the alpha position from before. This is where hydroxide can come, pull off another proton from there to form the enolate that then will complete the elimination reaction to condense our final structure. Again, aldol condensations intramolecularly, please make sure that they are 5 or 6-membered rings. Robinson annulation is not a new reaction. It's just a combination of Michael and aldol. But it's a long one.